Good afternoon, class. We are looking at Chapter 2, Limits. Here's Section 2.3, Limits of Functions at Finite Numbers. We looked at limits of sequences, limits of functions at infinity, and now limits of functions at finite numbers. Here's the synopsis of what we covered. A sequence is an ordered list of numbers or function f whose domain is the set of natural numbers 1, 2, 3 to infinity. Limit refers to the long-run behavior of a sequence, i.e. what happens to a sub n of a sequence in the long run. So the limit of a sub n as n approaches infinity equals L. You say that a sub n converges to L. If this limit is equal to infinity, negative infinity, or does not exist, we say the sequence diverges. And to find limits, we simply plug in an upset. There are a couple of theorems we want to discuss. The limit of 1 over n to the power of p as n approaches infinity is 0, as long as p is positive. The limit of r to the power of n as n approaches infinity depends on the value of the base r. If it's between negative 1 and 1 is 0. If it's 1 is 1, and if it's larger than 1, it goes to infinity. Geometric sequence, when we add them up, summation of a r to the power of n minus 1 from 1 to n ends up having the format a times 1 minus r to the power of n over 1 minus r. And if we take the limit of this expression, when r is between negative 1 and 1, because of this theorem, r to the power of n goes to 0. It simplifies to a over 1 minus 1. So a geometric sequence has a solution b sub n plus 1 is r b sub n. Recursively, b sub n equals b sub 0 r to the power of n explicitly, where b sub 0 or a are the same, and sometimes we use b sub 0, sometimes a. And if we add a constant to this, such as giving medication at a specific time step to patients, the solution b sub n is b sub 0 r to the power of n, just like that, and it adds this for this piece also, plus c times 1 minus r to the power of n over 1 minus r, again b sub 0. Finally, the definition of a horizontal asymptote for a function y equals f of x. If the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches infinity is L, then we say y equals L is the horizontal asymptote for the function y equals x. And now the new stuff, 2.3, limits of functions at finite numbers, finding limits by numerical and graphical methods. This one, this definition, we read, as we've been reading already, the limit of f of x as x approaches a equals L. Let's look at these graphs and learn about graphical approach to limits and what they mean, as we are interested in finding the limit of f of x as x approaches a. X approaching a is along the x-axis in all three cases. And in all three cases, as x approaches a from the left, we are moving in this portion of a graph and moving from the bottom to the top. From the right side, we're moving this way, coming down along the y-axis. And in all cases, the limit exists. And the limit of f of x as x approaches a is L in each case. However, what happens here that f of a is also L, there is no hole. This one has a hole, and f of a is not equal to L. Because we have a solid dot, the answer is B. And in this case, f of A is not even known, it's not given. So we say it's not defined. So part A, f of A is also L. Part B, f of A is B, which is not equal to the L limit. And part C, f of A is not defined. But in each case, regardless of what happens at A, the limit of f of x as x approaches A is L. Meaning, when we look at the limit, what matters is in the vicinity of that number, not exactly at that. Also, the concept of a one-sided limit. A function has a limit at A if the limit of f of x as x approaches A, this is read A from the left, is equal to L, and limit of f of x as x approaches A from the right equals to L. Because the two limits are identical, then limit of f of x as x approaches A equals A. And one more thing. If the limit of f of x as x approaches either A or A from the left or A from the right is either negative or positive infinity, then it gives rise to a definition for the vertical asymptote, which gives us x equals A. Now let's look at this example, everybody. Finding limits by numerical and graphical method. Guess what is the value of the limit of x minus 1 over x squared minus 1 as x approaches 1. We're going to call this f of x y or f of x, and note the function f of x is not defined at x equals 1. However, it's not important. Why is that? Because the concept of a limit says as x approaches 1. It doesn't mean at 1. So let's look at this from a numerical method. Let's evaluate f of x equals x minus 1 over x squared minus 1 with so many decimals, in this case 6, for values of x that approach 1 but are not equal to 1. So the table that we are going to use, the tables below give values of f of x for values of x less than 1 and x larger than 1. So for x less than 1, but remember, we're talking about the limit has to be very close. So even if we start with 0.5 and 0.9, even 0.9 is not close. 0.5, 0.6, 0.7, 0.8, 0.9, and we get closer and closer and closer. The more we add to the number of nines after the decimal, the closer we get. And we plug it into this expression and we get the following answers. For x larger than 1, we do the same thing. Larger than 1, 1.5, 1.4, 1.3, 1.2, 1.1. Way too far. Even 1.1 is way too far. 1 point too far from 1 as far as the limit is concerned. 1.01, 1.001. The more zeros you add before this one, you have to have a 1. The closer it is to 1, you evaluate. And then you look at, when you want to figure out what the limit is numerically, you look at this last one and you say, this is the closest number to 1. Closest number to 1 is this answer. This is the from the left. This is the closest number among those to the number 1 from the right. This is the answer. Accordingly, you should be able to see that the limit of x minus 1 over x squared minus 1 as x approaches 1 is 0.5. If you graph this function, and by the way, I remind you, when you graph a rational function, first you have to put it in lowest term, because whatever makes the denominator 0 is not necessarily a vertical asymptote unless it's in lowest term. And so what makes the denominator 0 and it's common, it creates a hole, and that's what happens here. So as we look at the graph, here's number 1. From the left and right, in both cases, we are moving towards this hole, which means f of 1 is not defined because there is a hole, but the limit is given as 0.5. Finally, the algebraic or analytical method is to simplify the rational function, because if you plug in, you get 0 over 0, which is indeterminate form. And the methodology is to factor. Notice the denominator is x squared minus 1, or x squared minus 1 squared is the same thing. And a squared minus b squared is a minus b times a plus b. We can factor the denominator into x minus 1 and x plus 1. These two cancel each other. We get the limit of 1 over x plus 1 as x approaches 1. And now if you plug in, you get 1/2 or 0.5. So you should always go with the algebraic method unless a specific question asks you for the numerical method or a graphical approach. One-sided limit. The function h is defined by h of t equals 0 if t is less than 0 and 1 if t is larger than or equal to 0. This is called the Heaviside function in electronics. So if you take the limit of this function, one-sided limit, as t approaches 0 from the right, then you use the greater than and it becomes 1. And so this symbol means that we consider only x larger than a. We read limit of f of x as x approaches a from the right. When we say a from the right, it doesn't mean positive or negative, because if you have a positive number, both sides is positive. For example, the left side is 4.9, the right side is 5.1 for number 5. If you have a negative number, both sides are negative. For example, negative 5.1 here to the left, negative 4.9 to the right. So this means from the right, and the limit of this function as t approaches 0 from the left, it uses the top branch because it's a piecewise defined function and it becomes 0. And this symbol means that we consider only x less than a, limit of f of x as x approaches a from the left. So this is understanding the concept of a symbol, the limit as x approaches a from the right versus from the left. Also, note the limit doesn't exist because these two are not identical. They must be identical. And finally, because we have the equality h of 0 is 1, that means at 1, at 0 is equal to 1. So if we were to graph this part becomes the x-axis normally, which is now the t-axis, and there's a hole here. And this part, y or h of t equals 1. So this gives rise to the definition of a one-sided limits. A function has a limit at a if the limit of f of x as x approaches a from the left is L, and the limit of f of x as x approaches a from the right equals L. Therefore, the limit of f of x as x approaches a must be L. Example 2, given the graph of a function g, state the values, if they exist, of the following. We are interested in finding the limit of g of x as x approaches 2. That's why we look at the one-sided limit. So this one is the limit of g of x as x approaches 2 from the left. This is from the right. So from the left, here's the left side of 2. This is the branch. it moves this way. We never get there, but we get very close. And the y coordinate is 3. Approaching 2 from the right. That means we move this way along the x-axis. We use this branch, and we are moving towards this hole, which has a y coordinate 1. These two are the same. No, therefore, the limit of g of x as x approaches 2 does not exist. What about limit of g of x as x approaches 5? We are going to do the same thing. We're going to look at 5 from the left and right, the one-sided limits. So the limit of g of x as x approaches 5 from the left, and the limit of g of x as x approaches 5 from the right. So as we look at those, we notice from the left, we move this way. From the right, we move this way. And in both cases, we are moving towards this point, this hole. We never get there. We get very close to that. So we get very close to this y coordinate 2 from the left and from the right. And therefore, the limit of g of x as x approaches 5 does exist, and it's equal to 2. However, if we assume this point has a y coordinate 1.4, that means g of 5 is 1.4, which is not equal to the limit. And ultimately what it means, it's not a continuous function at 5. But you want to distinguish between the limit and the functional value. The functional value gives us the answer at 5, precisely at 5, the dot. And also, what about 2? If you look at x equals 2, we don't have a solid point anywhere. So g of 2 is not given. We say it's undefined. By the way, normally we use d and e for the limit, undefined for the functional value. Here's the function, the graph of the function. We want to find the limit of f of x as x approaches 2, and we are going to look at the one-sided limits, limit of f of x as x approaches 2 from the left, and limit of f of x as x approaches 2 from the right. So from the left, we are moving this way. As we move this way, we are using this branch, and this one is moving towards this point. It will never get there, and that has a y coordinate of 3. Moving from the right side of 2, we are in this branch, and as we move towards 2, we are moving towards this hole. We never get there, and this hole has a y coordinate 1. And since these two numbers are not the same, the limit of f of x as x approaches 2 does not exist. Now we want to look at f of 2, limit of f of x as x approaches 4, and f of 4. When we say f of 2, that means exactly as at x equals 2. That means you look at a dot, a solid point. At 2 precisely, the answer is 3. What about limit of f of x as x approaches 4? We look at both sides. As we approach 4 from the left, that means going this way. As we approach from the right, that means we go this way along the curve. And as we move towards 4 both sides, we are moving towards this hole, which has a y coordinate 4. So the two are identical. They are both moving towards the same point. They never get there. So the limit is 4. And f of 4, we don't have a solid point. It's undefined. Infinite limits. This definition is illustrated graphically in the following figures. So when we look at these two, as x approaches a from the left and right, both of them go to infinity. This one from the left and right, both of them go to negative infinity. Therefore, in this case, we say limit of f of x as x approaches a is infinity. And in this case, we say limit of f of x as x approaches a is negative infinity. Similar definitions can be given for the one-sided infinite limits. So if we look at these two are similar to that in that they both approach infinity. This one from the left, the limit of f of x as x approaches a from the left is infinity. This one from the right, the limit of f of x as x approaches a from the right infinity. These two are similar to this. This one from the left, this one from the right. Limit of f of x as x approaches a from the left is negative infinity. This one, the limit of f of x as x approaches a from the right is negative infinity. Which means now we have a formal definition of VA, vertical asymptotes. Vertical asymptotes are in the form of the equation of a line, a vertical line, x equals a, if the limit of f of x as x approaches either a or a from the left or from a from the right is positive or negative infinity. For example, one of those elementary functions, and by the way, we should know the graph because it gives us a lot of information. It's y equals ln x. When we remember the graph, we remember, for example, the domain is 0 to infinity. From the graph, you see that the range is all real numbers. You see the x-intercept is 1, 0, things like that, okay? So the graph is important. And so as you can see from here, you have a vertical asymptote, which is the y-axis or x equal to 0. And you write the limit of ln x as x approaches 0 from the right is negative infinity. And the vertical asymptote has the equation x equal to 0, which is the y-axis. Here's the function. It's given in the form of a graph. We want to find the limit of r of x as x approaches different values, for example, 2. So I hope you see as we approach 2 from the left and right, in both cases, it's going down to negative infinity. For 5, from the right or left makes no difference. Here's the left, here's the right. So from the left or from the right, both of them goes to positive infinity. However, when it comes to negative 3, from the left, it moves down to negative infinity, but from the right, it approaches to positive infinity. All of them give rise to the equation of a vertical asymptote. This gives us x equals 2, x equals 5. These two, both of them give us the same answer, x equals negative 3, and those are the equations. So again, a quick recap. This one, x equals 2. This one, x equals 5. These two, x equals negative 3. That would be the equation of a vertical asymptote, reminding you of the definition that was discussed previously. Find the following limits, limit of square root of x plus 4 minus 2 over x as x approaches you. By the way, the numbers here refer to questions have been picked up from your exam review practice test. What happens when we plug in 0? If you plug in 0, you get 4 here. Square root of that is 2 minus 2 over 0. So I hope you recognize this as 0 over 0. And 0 over 0 is one of those indeterminate forms. So indeterminate form of 0 over 0. We have infinity over infinity. We have infinity minus infinity, and there are other forms. Please don't mix them up with 0, undefined, anything like that. It's indeterminate, which means you have to use your algebraic technique to fix the problem. And by the way, it is always the 0 in the denominator that creates a problem, and you want to find an algebraic technique to get rid of it. This has a square root, and the technique is the conjugate. I hope you remember the conjugate for a minus b is a plus b. So the conjugate for the numerator is the same thing. You just change this sign to a plus sign. So you can't just multiply by that, but you can multiply by 1. So you multiply by the conjugate and you divide by it. This expression is acceptable because this expression equals 1. So we are looking at a minus b times a plus b equals a squared minus b squared. First, I want to discuss the denominator. Because x is approaching 0 and makes the denominator 0, you're hoping to get rid of that because that's the problem. So you never ever distribute this. You just write x times the parentheses and you put that in a parentheses because you're hoping to get rid of the x. The numerator, however, you are going to multiply them through by a minus b times a plus b, resulting in the following square root of x plus 4 squared minus 2 squared. And that means x plus 4 minus 4. By the way, remember, if you have a negative number to the power of 2, that is positive 4. But if you have minus, 2 squared is negative 4, because in the second case, this negative remains. This one, negative gets raised up. 4 and negative 4 cancel each other. X and x cancel each other. If you plug in, this becomes square root of 4 over 2. 2 and 2 adds up to 4. So the final answer is 1 over 4. So to recap, when you have indeterminate form, you have to use some algebraic technique to get rid of the 0 in the denominator. Okay. But why am I looking at these two questions simultaneously? This one is the same, the two are the same functions. The limit of x plus 2 over x plus 3. The first one, x is approaching negative 3 from the right. The second one, negative 3 from the left. So if you don't pay attention the right and left, the numerator becomes negative 1. The denominator becomes 0 for both of them. Now, the numerator is negative 1 in either case, because when we say negative 3 from the right or negative 3 from the left, the numerator is very close to negative 1. And again, just to give you an idea, when we look at negative 3, the left and the right, for example, the left side for negative 3 would be negative 3.1. The right side, that means a little bit larger than that, would be like negative 2.9. If it makes it easier, put negative 3 here, negative 2 here. So my point being, both sides are negative. It's extremely close to negative 3. And the numerator in this case becomes like negative 0.99, and in this case, like negative 1.001. What matters is the denominator. So you have to figure this out, and I'm going to show you how you figure out the denominator, and therefore you end up with positive or negative infinity. It's important to remember, when you divide by 0, we used to say undefined. That's not what we are going to do in calculus. We are going to figure out positive or negative infinity. And when we divide by 0, it's one of them. It's not necessarily negative or positive. You have to figure out which one. So how do we figure it out? Let me show you. So in this case, if I go with negative 3 from the right for the denominator, let's say negative 2.9 plus 3, I get positive 0.1. So it's negative 1 over 0 from the right. Whereas here, for example, negative 3.1 plus 3 is negative 0.1, and it is negative 1 over 0 from the left. So this one is negative over positive, so becomes negative infinity. This one is negative over negative, becomes infinity, positive infinity. And that's the difference between the two. And this is a very simple methodology to do it. All right, how about here? Um, If you ignore the fact that it's 5 from the left, you get e to the power of 5. This becomes 0, 0 cubed is 0. But you can't ignore that. Why is it that you can't? Because you have to figure out the answer is negative or positive infinity. So how do we figure it out? 5 from the left or 5 from the right, the numerator class is either e to the power of 5.00001 or e to the power of 4.999999. It makes no difference. They're the same. Okay. But it makes a difference for the denominator. Let me show you. So if it's 5 from the left, example, remember 5, both of them are positive. The right side is 5.1, let's say. The left side is 4.9, let's say. So 4.9 minus 5, it makes it minus 0.1. So now this is 0 from the left cubed. And again, if you happen to have a negative number, for example, negative 5, and square it, you get positive 25. But if you cube it, you get negative 125. So therefore, this is 0 from the left because this is an odd exponent. And therefore, the answer is negative infinity. On the other hand, same question, and I change the exponent such that this exponent is even. So a negative number to the power of even is positive, and positive over positive is positive. The answer is infinity. That's the difference between the two. So it's a good question to go over that a couple of times. The limit of x squared minus 2x over x squared minus 4x plus 4 as x approaches 2 from the left. Now, if you plug in, you get 0 over 0, everybody. But generally, which is an indeterminate form. But generally speaking, when you have a rational expression or a fractional expression, if you can, you must simplify. So that means factoring. Obviously, the top is x times x minus 2. But what about the bottom? Recall, a squared minus 2ab plus b squared is a minus b squared, quantity squared. A squared plus 2ab plus b squared is plus b quantity squared. I hope you remember that. So the bottom is x minus 2 quantity squared. So this has got to do with the prior knowledge of mathematics and being comfortable with factoring. So we can drop the factor of x minus 2 from the top and one factor of x minus 2 from the bottom. And this is what we get. And now if you plug in 2, everybody, you get 2 over 0. But it's not 2. It's 2 from the left. So example, 1.9 minus 2 makes it minus 0.1, which gives you 2 over 0 from the left. Again, why is it important? Because this gives us the sign for the infinity. This doesn't, okay? This tells us positive over negative is negative infinity. So the final answer for this question is negative infinity.